So if you have a chemical reaction, you will be able to get the entropy of the chemical reaction by using the thermodynamic chart. So first, let's see if you remember this chart. So in this chart, you have thermodynamic quantities. So what that means is you're going to have delta H values, delta S or S values. You get the delta by subtracting. And you're also going to get delta G. Those are the thermodynamic quantities. Here's a delta H. Here's delta G. You will learn more about that later. I haven't taught you that. And there's the entropy. Okay. Now you might wonder, what does the little dot mean? That means at standard conditions, which is 25 degrees Celsius. Also, if it's gas, it's a 1 atm of pressure. And if it's in solution, it would be 1 molar solution. That's what that means. So if you guys remember, the delta H of formation is, for example, for Al solid, is the energy you need to form the substance aluminum solid, which is 0 because it doesn't take that much energy. If you combine the Al and Cl3, it'll give off this much energy when they combine from their aluminum and Cl2. That's what you get. And if you had a chemical reaction, for example, H2 plus O2 makes H2O, you remember, and of course you have to balance it, to get the delta H of the chemical reaction here, the total energy of the reaction, you do products minus reactants. Well, you do the same thing for delta S. All you have to do is, instead of using these numbers, you use the S numbers, products over reactants. Okay, what I want to point out are the numbers are a little bit different. First, the unit is different. Here, this is kilojoules per mole. This is joules per mole, not kilojoules, right? Because they're not as big, so they have them in units of joules. And also there's a K underneath. And you might wonder, why is that K there? That's because entropy is equal to the amount of energy put in at a certain isothermal temperature, that certain temperature. So the unit is J over K. Remember? And this is just per mole. That's why they call these molar entropies. Okay, if you look at the entropies, the numbers do make sense. If you have, let's say, a gas versus, here's the entropy of the gas, 174, right? If you had a liquid, do you think the entropy would go up or go down? Well, it's more ordered, so it goes down. If you have a solid, it would be even lower. Here we have the entropy of calcium as a gas. It's high. It's very chaotic in there. Chaos. High entropy. The solid would be ordered, low entropy. So if you want to turn calcium solid and turn it into calcium gas, well, what would happen to the entropy? Will it go up or will it go down? Of course, it'll be more chaotic, right? So it's positive delta S. Remember, positive delta S means more chaos. So if you use the numbers, it would be 154.8, which is this one, 154.8 minus 41.1. Remember, it's products minus reactants. So they're both positive initially, but you're subtracting this minus this, and you're going to get a positive number, which tells you when you turn into a gas, it becomes more chaotic, and that is delta S. Notice it's S in the beginning. When you subtract them, it becomes the change in entropy. Okay, so now you understand those. So let's go back to the lecture. So you know about molar entropies. So they're S's, and they're for every mole. This is S. Okay. Again, standard states, that's the little degree sign there, little dot. 1 atm, 1 molar, 25 degrees Celsius. As you notice as well, the entropy increasing in molar mass. So let's say C6H6 here is the heaviest, higher entropy. That's also because you have more electrons there, and those electrons, they can move around. You can take many pictures as they move, right? More microstates. Okay, so entropies also increase with the more complex the molecule is, because you have degrees of freedom or degrees of motion. So you have different types of atoms, and it changes. Okay, so here it shows you the entropy is products minus reactants. This just means if you have more than one, you add them all up. That just means sum. And of course, if you have 3 moles, you multiply it by the number of moles, and then you get the S from the chart. Okay, and let me show you how to do that. Here's an example. If you want to get the delta S for making ammonia, well, you write your equation. Okay, you get some nitrogen gas, you get some hydrogen gas, you make ammonia gas right here. Balance the equation. There's a 3 there, a 2, and a 1. Okay, you look up the numbers from the chart, and 2, if you look at the thermodynamic chart, I found it over here, and 2, I circled it, it's 191.5. Ammonia is that number, and H2 is that number, so I went ahead and put those numbers ahead of time. Once you have those numbers, I'm going to draw a line here. I'm going to multiply them by the number of moles. So when you do that, you're going to multiply this by 1 mole, and this will cancel here. You're going to multiply this by 3 moles, and the moles will cancel. And you're going to multiply this with 2 moles, and the moles will cancel. Okay, when you multiply this, you're going to get 385.0, and the units, it is J over K, as you can see, the amount of heat transferred at a certain temperature. Okay, when you do this math over here, you're going to get 583.2, again J over K. The final formula is, and what you did is you just added them. See the sum? I just added these together. I summed all of them and I multiplied it by moles, okay? And so I'm going to get the change now. So the formula for that is products, reactants over here. I'm going to use it in blue. Products minus reactants, and that will give you delta S. So the products is this number, 385. Okay, so this is 385 J over K for the products, minus reactants is 583.2 J over K. That will give me a delta S. Wait, before we get that, let's predict it. Is it going to be positive or negative? What do you think, pause the video? I think it's going to be gas turning into a gas. You used to have 4 moles of gas. Now you have 2. Uh-oh, it became more ordered. So I think it's going to be negative, delta S, because it's more ordered. Because you have less people at a party. So when you do this, yes, I do get a negative number, and it's negative 198.2. Okay, so what does this mean? This is the amount of energy at that temperature, right, for each mole of this chemical reaction. This is the entropy of the chemical reaction. Let me rewrite that. It's really hard to see. 198.2 J over K for every 1 set of this chemical reaction. For every mole reaction. Okay, and that's your unit.